we would be having the first session from 3 p.m. And for this session, we are having a very eminent personality from the Rustamji Institute of Technology, Gwalior. So, Professor Prashant Kumar Jain. So, if I introduce a little about him, so Professor Jain is holding a rank of professor and is serving now as the principal of Rustamji Institute of Technology at Gwalior. So earlier he was the professor in the Department of Mechanical Engineering at IIIT Jabalpur. He has uh, done his PhD from IIT Delhi, and he's having more than 25 years of teaching experience. Earlier, he has served as the assistant professor in the Department of Mechanical Engineering at Delhi Technical University also. And he has done a lot of work in the field of additive manufacturing, and various unique works have been I have seen his work. He has established work here in the IIIT Jabalpur with various projects he is dealing with. So he has incurred the projects from DST, BARC, and various funding agencies. He has more than 200 public publications to his credit, and published various patents as well. And he's having almost 4,000 citations as of now. And his academic and research profile is very great, and we are very, very fortunate to have Professor Prashant Kumar Jain in this FDP as our first a keynote speaker. So I welcome Professor Prashant Kumar Jain to deliver his lecture. We warmly welcome you, sir, and we are very fortunate to have you on this session.
So good afternoon, Professor Prashant Jain, Dr. Sachin, and everyone over here. And
Good afternoon, ma'am.
I'm happy to see that Professor Jain is going to deliver. To add to what Dr. Aman said, he is still a member of our institute. You said that earlier he was working. In fact, he is on leave from the institute.
Yes.
That's so.
Okay.
Welcome. Yeah, thank you.
So thank you very much, Oja ma'am. She's the IC coordinator of AICT Academy at PDPM IIITDM Jabalpur. So before I request Professor PK Jain to start, I just want to describe a little bit more about him. So Professor PK Jain is a professor in Mechanical Engineering Department at IIITDM Jabalpur. And he is currently on deputation to Rustamji Institute of Technology, that is the BSF Academy, Gwalior, as a principal. So he has more than 25 years of research and teaching experience at UG and PG level. He is graduated in mechanical engineering from Dr. H.S. Gore Central University in 1995 and completed his master's in advanced production system from Samarth Ashok Technological Institute. He has received a PhD degree in additive manufacturing from IIT Delhi in 2009. Dr. Prashant Kumar Jain was previously with DTU, Delhi Technological University, as a faculty in Mechanical Engineering Department. He also served as he also served in IIT Delhi as a project scientist and research associate, where he was engaged in the research work on error compensation, CNC machining. He has also discharged his duties on various administration positions at IIIT Jabalpur, just such as a warden hostel chairman, placement cell, head of the ME discipline, dean students, dean research sponsored project and consultancy, faculty in charge PSC, faculty in charge visitor hostel, member of Senate and member board of governors. He has more than 200 publication at his credit in international peer review journal. He has H index of 34, 3,500 and more citations. He has been member and editorial board member of different reputed international journals. He has served as a chairperson of different international conferences. He has professor has guided 11 PhDs and 28 master's students, while several are still going on. He is having 7 research consultancy projects, and several of them has been completed, and a few are still going on. His research interest is usually on geometrical modeling, CAD/CAM integration, CNC machining, incremental sheet forming, computational geometry, additive manufacturing, rapid prototyping, and nanotechnologies in manufacturing. Now I welcome Professor P.K. Jain to please continue the session. Thank you very much.
Thank you, Dr. Sachin, and thank you, Professor Oja Madam, for giving me this opportunity to remain connected with the academics and have this session with the participants of ICT Academy. Let me share my screen, and in the meantime, I would request participants if you can switch on your camera for a quick view of each one so that we can take up this session in a more interactive way. I can see Dr. Sachin, Dr. Aman, and myself, and I see Professor Oja in this session. So I would request remain all the participants. For a few seconds, you may have your network issues, but we have to keep this session very interactive so that we can discuss and learn from each one. And this is the mandate of ICT Academy as well. We keep it very, very interactive. Advance screen. Okay. I'm sharing my entire screen. You also require to keep on typing in the chat box. So that in the sometime we will run some software, sometime I will show you some simulations. Yeah, I can see Ulhas. Yeah, Jitendra, Anand, Anil, Vibha. Dr. Sachin, I think participants are allowed to unmute in between.
Yes, sir.
So I would request all the participants to unmute, and then we will begin with this session, because Dr. Sachin has given me this opportunity to speak first due to some internal arrangements. I would be taking you to this topic on developing novel induction heating assisted additive manufacturing technology. So I see very ambitious content has been put up for this FDP, and many vast things are going to be covered under this. So in this session also, we will start with little bit basics of the 3D printing, additive manufacturing, then come up what kind of programming skills are required to have this implemented. Then I will take you to the MATLAB screen also, so that you can see how the programming has been done to generate the data to control the CNC machines and develop new CNC setups for metal printing instead of polymer printing, which mostly the commercial machines does. Okay, so you can go to the chat box and just type hi. Okay. Did site show meeting mode pause layout? Yeah, I have enabled the chat open. Okay, in this I may not be able to run from two parallel screens, right? I hope you can see the only PPT screen. I can see Mukta Tripathi only in the chat box, right? Yeah, few more. Jitendra, yes. Okay. Okay, very nice. I can see few responses in the chat box. So I will keep it on the side panel. Okay. So let me begin with this, and you please continue to type on the chat box. Okay. So what we do in this session, we have taken the induction assisted additive manufacturing and their development technologies. So let us begin with the additive manufacturing. Which portion you know? I would be just questioning something. You can just type in the chat box yes, no, or whatever your comment is there. Okay. So we begin with the product fabrication. Generally, say for example, what the product I have on my screen, if you want to fabricate this, immediate thing will come in your mind that we can go for the machining. So like this, you have the product and you can remove the material from top to bottom and you will get the machining done, right? Then we have the joining processes, right? So you know welding, soldering, iron, etc. We can go ahead. And the most common process is the forming process, where we take this forming, so maybe the injection molding, die casting, or whatever the forgings we generate, right? This is the most common. Now today what we are talking about the additive manufacturing or the rapid prototyping or the layered manufacturing, right? So you see, we have now this time the bottom up approach. Okay. So in case of this bottom up approach, we are depositing the material layer by layer and creating the layers towards the top. Okay. So like this. Okay. Now you can see over here what the advantage we can gain from this. So in additive manufacturing, what you get? Process creates a model of an object directly from its CAD model by depositing the material in layers. So see, this is the side or one panel of the hair dryer gun. So from this hair dryer gun, you can see over here. Otherwise, if you don't go for the rapid prototyping or 3D printing, a lot of things are required. And in for visualization as well, you may require so many drawing sheets to convey your idea to the manufacturing shop. Then you have to create pattern, molds, etc., and perform this casting, and then some finishing operations as well required. So you see in this case for polymer, so in this case, you see here, entire product can be made within the with your hand. Okay, so this is the advantage you are going to get in this. These screens are not adjusting. So why we go for the additive manufacturing? Immediately when I say additive manufacturing, two things comes in our mind: machine additive, then why not subtractive? Or what is subtractive? So we have both the ways available. Machining is a subtractive process. Begin with a solid piece of stock. The machinist is going to carefully remove the undesired material. Okay, so you will get the desired geometry in the head. So subtractive means subtracting something. Right now, what happens in this case of subtractive machining? Some of the complex part geometry, right? Very difficult to go for the machining processes. May be very exhaustive, may be very time consuming, and very, very expensive. Suppose you are working on the brass, where mistakes are very costly. If your part is rejected, are mismatched with the desired dimension, then you have to reject that piece and the material cost is very high. Sometimes what happens, the workpiece size is huge and you are going to have the precise part fabricated might be very, very small. Okay, so in that case, the machining process will become very, very expensive. So even some of the part you can see in the picture, very, very complex. You may not be even able to produce them using this machining processes. In this case, look at this. Okay, can you see I am writing on the screen? Say yes or no. You can unmute and you can respond because now I have closed the chat box.
Yes, I
Should
can
have.
observe. Yes, we can observe.
So you can see here, in this case, this 5-axis machining, even the machine, you take the 5-axis machine. But in some of the areas, this machine tool cannot reach, right? So it will become very difficult. On the other hand, here is the additive and subtractive processes, both. So I will tell you, in additive manufacturing, a polymer-based and metal-based later. So you have the two options, right? Two part material and the support material, and it will move like this to deposit the material, right? So you can easily build this part and later on this support material is removed. Okay, that I will take it again in the next slide. So here you can see why we go for additive manufacturing, to just avoid this complex part geometry, are very exhaustive, time consuming, or expensive. So we can go, right? So what happens with the additive manufacturing? That complexity of the part, right, is no more a limitation. Right? So what we say often, a picture is worth 1,000 words. You see the communication tool. You don't want to communicate something by just paragraph writing. Okay. You want to draw something. Why we want to draw something? Because we want effective communication. What is that effective communication? Instead of text, you are trying to use the picture as a tool. So here what is happening with this rapid prototyping of the polymer material, you got this opportunity to print a model. So when we say a picture is worth 1,000 words, a model is worth 1,000 pictures. That's the advantage you are going to get with the additive manufacturing. And that you can see in the reality like some hard model, right? Like this fully functional springs, engine block, okay? Like you see the toy. Let's see this temple model. Here you can see a lot of stairs are there. We will talk little later, talk about these things. Okay. So now I'm coming to very quickly going to tell you about the two processes, fuse deposition modeling. And why I am talking about fuse deposition modeling, because this fuse deposition modeling has given the idea how we can go for the metal additive manufacturing, right? And why to go for the metal additive manufacturing, which is just we have tried. In the subsequent part of this session, I will show you some more videos of our aluminum printing process. That this is commercially available, easily available. Polymer testing, right? So process is solid based, support structure not required in this case, the capable for handle a wide variety of the material. Okay, so look at this. This is the nozzle part and it will form like this. So every successive top, it will do this. And how the process is working? Two wired spool are there, two nozzles are there, heated nozzle. The red color is the heater is there, and here are the roller. Okay, you can see over here, here are the roller. So these two rollers are there, right? Okay, so from here, this wired spool material is coming and pushed by these rollers through the nozzle, and here this is deposited, right? So this is the part material, this is the support material. Okay, and with this support material, this nozzle. So here is the build platform. Every time when this first layer will be deposited, this platform will go down. Okay. So here the part material, this part nozzle will work, and everywhere just like Mehendi cone, it will deposit the material. And for this overhanging feature, you require a support. So for this overhanging feature, you require a support. This support material will be deposited in this way. Okay. So once this first layer is completed, this platform will go down. Okay, by one layer. Say in this case, it is 150 micron. So by 150 micron, it will go down. Okay. And you see, based on this kind of model, you are going to predict for the, you see the architectural model. See the house model. This is through the ABS material and printed through the FDM process. Now, like see the large model, your boiler model, the blades, etc., the full component you can see over here. This is built by the FDM machine. Okay. So at this stage, I would like to know how many of you aware about the FDM process. Accordingly, I will talk further. In the meantime, please type in the chat box. In the meantime, let me run this video. You can see my screen, right? Can you also see the sound? Can you listen the sound?
No, we cannot listen to that.
Okay. I think sound somewhere might be setting. Aman, can you tell me? So
Yes, sir, I'm
meeting.
looking after it.
Okay. Otherwise, I will explain. Nothing to worry.
It's checking.
No, it's video only. Okay, let us continue. We will see system sound we wanted to transfer actually. We'll look for the system sound.
Sir, it is from your end only, sir.
From my end, yeah, that is what I'm looking. Pause, annotate sites.
So if you have connected any earphone, that may be to unplug if you are taking the
No,
lecture.
not connected. I'm not using earphone. I'm directly using laptop.
Okay, okay.
Okay, leave it. Nothing. I will explain. Let to continue with this. So see what I'm trying to show here. You can see here, this is the solid model. And so first we export it as a STL file. And with that STL file, so that aeroplane model has been oriented and now it is sliced into the planar sections. So every section is a planar section, contour information we have. Then this is the support information. Now see the top view of every contour. You can see here how the nozzle is printing in actual practice is not that much fast, right? But you see here, whatever the geometric model you have created, that geometric model is now available and we can build it, we can print it, we can have in it our hand. Okay, that's the important. Now I'm coming back to my question. Right. How many of you are aware about the FDM process? 15, 19. Your voice is clear. Okay, voice is okay. Anyone who is aware about the fuse deposition modeling process? If you have any question in this process, please let me know. What we are going to tell you, here you see the plastic wired material spool form is heated and extruded through the heated nozzle to deposit on the platform, right? And what technology I'm talking about, the metal additive manufacturing, we have tried to, instead of polymer material, we should use the aluminum material. So we should use the aluminum wire and deposit it. And you can pay attention and if you thought that instead of what were the challenges if instead of polymer material we wanted to extrude in the same way the aluminum material. Anybody would like to say something?
The temperature to melt, high temperature required for.
Okay, you said high temperature. Okay. Okay. Anyone else? Anyone else would like to say? One is the temperature. Okay. You can type in the chat box also. Then we will move to the selective laser sintering process, right? So look at this. This is, we talked about the additive process of polymers. Now look at this. I am showing you the schematics operation of the SLS machine. SLS is what? Selective laser sintering process. Okay. So why we call the selective laser sintering process? SLS. Sintering. So we are not completely melting the material, but we will sinter them. So that is just below the melting temperature and we will able to join the particles to particles. So particles join together without the complete melting. So neck formation will be there and one particle will join with the other particle. Okay. Then schematics and operation may you see just here what we do in this machine. This is the recoater. Okay, and within this you can see the center portion. This is the recoater. That is the recoater, right? So material is built on this recoater, filled in this recoater, and this recoater will move left to right, right to left, one by one. And every time when this layer is formulated, this laser is coming on this. Okay. So what happens in this case? This recoater record the fresh powder material, okay, on this platform. Okay, then inside there is infrared heaters are there. So what happens once this material is recoated on the platform with uniform thickness, say around 150 micron. Okay, inside this infrared heater as there, they will be switched on. So they will heat the entire environment inside this chamber and make the same temperature or thermal equilibrium at the inside this build chamber. This is the build chamber. And this build chamber, this is the galvanoscanner. What is the role of this galvanoscanner? It will take this laser beam and divert through the lenses in different areas, right? Different areas means this will scan like this. See on the second figure. This is the galvano scanner, and this is the laser beam coming.
It's similar to powder bed fusion, right, sir?
Okay. So that's why we call it selective laser sintering process. Okay. Okay. Then what happens after the one area? You can see over here, this is the solid portion. Right? This is the solid portion. Once this is solidified, this entire platform will go down. Okay. So you can see here, this is the solid material, and either this side you can see here, the unsolidified material, means that is the powder. Okay. So here in this case, you don't require any support material because unsintered powder will also provide the support. Okay, so once it is solidified, then it will be again recoated. So every time what happens? Recoater done, then laser comes, scan the path, preheat the material, post-process the material, and after this solidified material, this every time this platform will go down, and then once it is go down, then again recoater comes left to right and right to left and have the new fresh layer. Can you think that why I am talking about 150 micron layer thickness? And what would be the particle size in this case? Anyone? What would be the particle size in this case?
150 microns.
Pardon?
150 microns.
150 micron. Okay. Anybody else? That is why I'm trying so that we can relate how this layer thickness will be derived by the particle size. So that we can understand when we talk about the aluminum printing, we can understanding how difficult or what kind of challenges one has to overcome to develop the new technologies. Anyone else?
Sir, 50
You
to
can continue
200
to type in
microns.
the chat box.
50 to 200 microns.
50 to 200 micron. Okay. Look at this here. V says 150 micron layer thickness. Okay. So particle size cannot be more than 150. If it is 200 and this is the layer thickness, right? So if you want 150 layer thickness means this much material is already above. So you cannot formulate this layer, right? Another issue is with this, for this layer thickness, you have to keep 40 to 60 micron size so that three particles, right? This will be the particle arrangement. So these particles will be arranged like this. So at least three particles will formulate a layer. Otherwise, if you take 150, then this particle, this particle, this particle, and now you see the lot of hollow spaces there. What about this space? Right? This will not be filled. And if you put the laser also, then it will join, but not completely join. So what happens? At least three idea is this. So three particle size is there to formulate one layer. Right? Here the molecular weight also plays the role. Otherwise, you see here, if you want to send, say you can easily make a layer. But suppose I will give you the talcum powder, you will not be able to formulate a uniform layer thickness, right? And the moment laser comes from the top, what happens? The talcum powder will spread over. So it will be discontinuous. You will not be getting this kind of continuous layer, right? Yes, 20 to 80 micron. So generally we keep it 40 to 60 micron. Okay, so this is happens with the selector laser sintering process. Okay, now see what happens in this case. Powder based process. Previous one was the solid based. Material was in a solid form in a wired spool. We have developed the CNC machine, which we have converted into the 3D printing machine, where instead of wired spool, we can use the pellets. That gives us idea why to only have the pellets. Why can't we even go for the powder? And that lead to why can't we have the aluminum printing just like this plastic material. So here what happens? Here we have in this case the powder material. FDM, what happens? We have the wired material, right? Now let me talk what is the energy source in the case of FDM process. How the polymer material is melted. Anyone?
It is heated, extruder heating, nozzle, semi-solid state filament.
Very nice. Nozzle is there. So you can say resistance heating is used. Around the nozzle, we put the resistance bend heater. So by supplying electric current, resistance heater is there, just like our electric iron, it is heated and it is melt down the polymer. Right? Now look at this. In this case, we don't require the support, because what happens in this case, unsintered powder will be there to provide the support. Okay. So see this video. Can you see the video?
Yes, sir, we can see.
Look at this in this video. Some of the tensile specimen we are printing. So these tensile specimen, you can see with the different color, or you can see the darker color. That means what happens in this area, the material is solidified. The material is joined together, right? And this is the powder bed platform you can see, okay? And this laser light has become reflective because for some experimental purpose, we have mixed nano clay with this polyamide 2200. This is the nylon material. The commercial name is polyamide 2200. Okay, so 40 to 60 micron size of the polyamide material. Okay, let me continue this video. See here. See here, this is the recoater. This recoater has spread the new layer. First layer after solidification goes down and the new layer has been built up. And this is the light is sparking, immediate light you have seen. This is the infrared heater. So that infrared heater will keep the new layer heated just below the 4-5 degree centigrade temperature. Okay, why 4-5 degree centigrade temperature? Because in this machine we are using a 50 watt CO2 laser. So that CO2 laser has to provide the remaining energy at a particular spot so that it will be sintered, not fully melted, but only the sintering. So you see how much precise control is required in positioning, in recoating, as well as in the laser solidification, right? So that only that 150 micron layer, which newly has been established, is to be melted and remelted with the previous layer so that it can join with the previously deposited layer, right? And you already understood why we don't require the support, because here the unsintered powder is there. That unsintered powder will provide the support to the overhanging faces. Okay, so see here, this is the solid. Now see the example, what kind of parts you can make from it. Like look at the car seat, look at the metal. Now this is what I am showing you is the powder based. So 40 to 60 micron. Now see some of the component on the right side. See here, these are the metal component, right? And you see in this case, this metal component. You see, otherwise, if you don't have the additive manufacturing, how you are going to make this part? How many small parts you have to take for the part build, or say for the casting, or how after the centering you are going to remove this part. So every time you require the investment casting because you may not be able to reuse this. Similarly, see in this, how many parting line are there, or how many different surface and different angles are there. So because of this typical different multi directions of the components, you cannot do the CNC machining. And since you are not able to do the CNC machining for this part, you can go for 3D printing. And in the 3D printing as well, you have to properly design and understand. Okay, so that's how the metal deposit. Now in the metal here, we take the 40 to 60 micron powder. In the case of metal, we can have to take 20 micron size particle. Now this is belongs to steel, 316L steel. Okay, so see that steel has to be in a powder form first. That is the big casting effect and cast challenge, right? Whatever the material of metal you have, it has to be pulverized and their particle size be maintained around 20 micron. That's the big challenge, first thing, right? Now look at this, what we are trying to make it here, two things. FDM process, material is in the plastic and in spool form. So what we are trying, material should be in the metal form and in the spool form. Why? Because you see in the selective laser sintering process, what happens? Metal powders can be there, but the powder making charges will be very high. Further, whenever you go for the support structure, say for example this, so this much material will not be solidified, but it will go through the heating cycle. Once it is going through the heating cycle, it may not be reused. So that much material will be wasted even without the part. So to avoid all these things, we have thought to develop for the aluminum printing and with alternative energy sources. Okay. So this is, we have talked about the FDM process and SLS process. If you so far, if you have any question, please ask that the moment. Then we will come what is the requirement for developing the new machine or new technology. So what kind of programming we have done or what kind of programming you require, that we will take up. Anyone?
Is the
You can
particle
unmute
size
yourself or you can type.
is the particle size in metal materials less because of density as compared to a polymer?
Yeah, because of the density as well as and requirement of the layer thickness. Actually, this is directly connected with the layer thickness. If you have the spherical shape, so if you have this size of material, right, then lot of space. Instead of this, you have this much material. So what will happen? The arrangement will be like this. So what happens? This gap will be become smaller. That's the reason, right? So metal case, we have around 20 micron size. You can find lot of papers are available for stainless 316L material for additive manufacturing. Okay. Anybody else? You can type also. Okay.
हेलो
So
हेलो
let us
सर।
move. हाँ. Yes.
सर मेरा एक क्वेश्चन है कि जो स्टील है जैसे 316L या इस टाइप का कोई स्टील है, इसको पाउडर फॉर्म में कैसे कन्वर्ट करेंगे? क्या क्या प्रोसेस हो सकते हैं? कैसे उसको रिसीव कर सकते हैं पाउडर फॉर्म में?
Okay, so that we have to go for powder manufacturing techniques, pulverization. Let's not divert at this moment because now we want to take the programming, how to get this contour information. For anything, okay, let me go for this. Pulverization you have to do. So there are many methods on the pulverization where we can form the powder. I'm quickly going to that portion first and then coming back, so that you can see how we are going to print the aluminum and why these two techniques I have talked before going directly to aluminum. See, this is the our build experimental setup, right? The powder machine, the polymer material you have seen how it is depositing the material. Now see what is happening with the metal. This is our development experimental setup which we have developed in the lab. See here, this is the nozzle is there, extruder head is there, nozzle is there. Instead of resistance heater, we have the induction heater right now. So these are the copper coils. And you see here inside this, the nozzle is there and it is moving and depositing the aluminum just like the plastic. So see here, the plastic was printed around 220 degrees centigrade. This aluminum is printing around 600 degrees centigrade. And it is highly reactive material. Okay, so immediately जैसे ही कुछ आता है इनका ऑक्सीजन पे चेंज हो जाता है. So oxidation will become and that will not allow you to join the material. So that's why it has become more challenging. You can see here this on the back, on the bottom side, you can see here this is the ball screw on the bottom side, right? Chain conveyor system. This ball screw is rotating this table. So the positioning is done in XY position, and for Z direction, the table is coming every time one step down. Okay, I hope this will clear picture something in your mind that what we are going to achieve. Right? So let me have from the beginning. This is the scene with the metal additive manufacturing. Okay, so now I'm coming back to the principle of additive manufacturing after talking two processes. Okay, this is the CAD model you are going to make. Okay, you want this CAD model after designing, you want to make a print from the any machine, maybe metal machine or maybe the polymer machine or maybe the extrusion based or maybe the powder based, whatever. Okay, so this information is stored in computer in a form of a picture or form of a geometric model. Okay, so with this geometric model, you need to find out this information because now every time you are going to build a layer. Yes or no?
Yes, sir.
Right? So once we get this information in the layer, then we will square it to make it the prismatic size of each and every layer, because layer cannot be built in this way. Okay, this is something like you are building your house. So suppose even you take these two layers, that your layer should be like this. Okay, so everything is now made in the form of a stairs, so that every time you can deposit the material in this area. So the moment you take the material deposition in this area will be filled. Similarly here, so the your nozzle will come and deposit this area. Okay, so we say CAD model, slicing the CAD model, squaring the edges of the model. Now you see, once these squaring edges has been done, then you will deposit the material or cut the material in this shape. Then you start joining them. So staking and pasting of the layers. Okay, once we join them, what we are going to receive? We will receive this product. What the unusual kind of difference you can observe in the first model and in the final model? Anyone?
Curvature is not there. Curvature. Curves. The
Okay.
radius.
Okay. Okay. Anyone else?
The circular hole is not there. It is oblong. It is a different shape. The one on the hub.
Okay. Very nice. Very nice. You see, this curved surface is required, but here it is not. Why it is not? Because everything has been converted into the stair. Suppose you have this kind of material and you can print only in the stairs, right? So this shape cannot become. What happens only every time when you print this layer and your nozzle come up to this layer, so this material will be solidified. For this much. For this much. This much material in any way you are going to leave. Got it? Agreed to it or not? At least
Yes,
five
yes,
responses.
Yes.
5 responses. Let me go back to the chat box. Yes. Yes, Manish, Ulhas, Anand. 3 responses, 4 responses, Vivek Gangrade. Yes. One more response. This is what we call is the stair-stepping effect. What will going to happen? Everything will become the stair-stepping effect. Okay. Now look at that. Let me come to the process chain. What we do for this information, what is required? You want a cross section to get this contour information, right? This contour information to be get, then only you can do the square edging. And then once you know this contour, okay, then you can formulate this nozzle path. Okay, so our requirement is first find out this contour information. Contour information is also like this is the model. So you are cross sectioning one by one. Got it? So coming to the process chain, your computer model, you are creating a geometry, tessellating it. Anybody know about the tessellation? What is this tessellation?
STL format.
Triangulation, sir.
STL format,
Triangle.
okay. That is okay. STL format. After tessellation, file is saved in the STL file. But what is this tessellation? Or what we does when we save any component in the STL file?
Triangulation. More the triangulation, more the file size. Lesser the triangulation, coarser the file size, and the minimum file size.
Okay. Anyone else? Anyone else? Tessellation is a piecewise approximation of the surface. ये surface था आपके पास ball, आपने इसको triangular piecewise approximate कर दिया. This can be a triangle, this can be a rectangle, pentagon, hexagon, anything. But we opt for a triangular because it is the plane which can created by the minimum number of sides. 3 sides required to minimum to create a plane. And another thing, if you have the 3-side plane, means a smaller side plane, that you can maximize the area covered under this tessellation. Say, for example, suppose it might be a sphere, okay, like this. And you will divide into the 4 triangles only. So what will happen? This much material will be removed. Got it? But instead of this, if you have the 8 lines, then what you can do, we can have this kind of like this. So you can, instead of this 1 line, you can convert it to 2 lines. This much material or this much volume will be removed, right? So you have saved more volume so that you will be more closer to the desired design of the designer. So that's why we opt for the triangle. Is that clear? And that's why we call it triangulation. Okay, that is the triangulation part. Okay, so this is basically the piecewise approximation known as tessellation. After this tessellation, we have to do the slicing. So this tessellation is not doing anything, but it facilitates the slicing. So what happens now, slicing is not done with the equation of the sphere, but the slicing will be done with the equation of this plane. And further, this plane can be taken into 3 lines. So suppose this is the plane passing through this triangle. You can find out this intersection point, this intersection point. And similarly, you can take all multiple triangles and find out these two are whatever the number of points coming, maybe sometime 1, 2, or maybe sometime 3, hypothetically. So you can have this. So that will help you to make this contour information. Okay. यहां तक किसी कोई डाउट है? Any question? No, so we continue. Okay, look at this, the tessellation. See, more practical exam. Can you see the cylinder on your screen?
Yes, sir, we can see.
See another cylinder. Can you identify what is the difference in these two cylinders?
Second one is tessellate.
Okay, anybody else? Anybody else? Two cylinders on your screen.
In the cylinder, there are triangular. On the face,
Yes.
there is triangle,
So,
and
right.
further it is extruded.
One first cylinder is completely
Yes.
sculptured surface, circular surface, or it can be anything. Okay.
Yes.
And another is the tessellated one, triangulated one, and every surface is now triangulated. Okay. So you can see here, once you triangulated, once you can do this slicing. Suppose say for this plane, you want to intersection. Here you have to work out with the full equation of a sphere or surface, you can say. But here what happens, the surface is divided into the triangular plane, and that plane itself is now two straight line. So you can easily find out these two contour points, right? And at the आपको sorry ऐसे करके polygon मिल गया. Like this. Okay. Now this will give you the contour information. Now this is what somebody was telling here. If you have the more number of triangles, this contour will be more and more smooth, more and more close to the desired geometry. Okay, so that is one, the tessellation you have done. That is third, you have done the slicing. After that slicing, you got this contour, right? Now you are going to generate this either in case of a nozzle path, and if it is a laser, then this galvano scanner will generate the path, right? So slicing done, then generating the laser path, scanning path. I will show you in the MATLAB how to do it. Then the post-processing. Okay, so post-processing will remove the support structure, any other unwanted material or something, or suppose some support structure is there in the So see how we are going to implement it. The first model you can see, this is the Pro-E model. This is the tessellated model. Can you see here the different triangles are there? What we have talked on the top surface, you see only 2 triangles are sufficient. But here you can see here sculptured surfaces, curved surfaces. So more number of triangles are there to keep very close to the desired surface. Okay. And on this side, you can see here Okay, so that's how the STL file working. What we have done, we have taken this model, we have read this model into the MATLAB. Now see, in this case, what we are doing, we are taking it to the intersection point. Can anybody tell what these blue color dots are showing? You see, every triangle is shown as now as the red color lines in a form of triangle. See, whatever here is there, this is the triangle, right? Triangular face you can see over here, right? This triangular face is now represented here as a triangle. Okay, and this the green color is the plane, and the black color you can see the contour information of plane. So you can guess what this blue color
Intersection.
dot is showing.
Intersection points.
One is saying intersection. Anybody else?
Intersection points, as you had told earlier.
Okay. Yeah. Anyone else? At least 5 responses, so we can continue. Okay, look at this. After this, what we will do? See, what is this diagram showing? Blue color lines are there. We have connected all the intersection points from one each other. Okay, but this information is not at all useful for us. Okay. Right. So what we have to do? We have to join these points in some logical sequence, right? So that you can see here in these points, this blue color contour is showing the external contour. This red color contour is showing the internal contour, like this. See here, we are cross section this point here. So once we cross section, you can see this area. Right, inside this hollow material is there, and this is the solid part. Similarly, here is the solid part. Okay. So that is how we find out the internal and external contour. Then the one task remaining left is the getting the tool path generated. Okay. So tool path generated, we can apply some logic. Suppose my laser is moving like this. At the first intersection, I can say laser is switch on. So laser will be switch on and this area will be solidified. And the second intersection, we can say laser has to be switch off. So laser is off. Now up to this point, laser is off. So no solidification take place and you don't require solidification in this area. Then again, laser is switch on, switch off. This area switch off. Again, switch on up and this area will be up to this. Like now suppose laser is passing through here. What is going to happen? This much will become solid because switch on, off. Then again on, off, on, off, on, off, on, off. So this much area here solidified, here it is solidified, here it is solidified, and here it is solidified. Got it?
How does it differentiate between the solidification, the solid part and the hollow part? Is that red and blue?
Okay.
What differentiating it?
You can do it. Look at this here. In this solid model, the very first model, you see here, there is a hollow portion, right? Inside this is hollow portion. So you know here by visual. Okay, please repeat your question.
Yeah, I saw the model. I understood the part. It is hollow there, that part. But how does the energy source come to know that this is to be filled and this is not to be filled? Is there any?
Yes. Very nice. Energy source will know from your computational algorithm, your software. So look at this here, what we have done, we have intersected. Okay, then we got all the intersection, then we got all these points like this, we have joined them. Okay, then we have developed some logical algorithm so that we can identify this is the external contour, right? Can you notice this is the external contour? Okay, got it? Is the up to this point it is clear? That is the external
Yes,
contour.
yes, sir. Yes, sir. Yes.
But for
Now
that, for
inside
that
this,
particular slicing plane, that is external contour.
yes, yes, right, absolutely right. For a particular slicing, particular height, particular contour, this is the external contour. Okay, now see, this is the internal contour. Okay, this red color. Is it okay?
Yes, sir.
Okay, then again, this blue color is the external, even though you can say it is internal, but because once it is internal contour, so the second one which is inside this, you can relate from here, this will again become external, right? Then this will again become internal contour. Is it okay?
Sir.
So right now on this point, you have the 4 contours, okay? 2 internal, 2 external.
Yes, sir.
All participant, is it okay?
Yes, sir. It is okay, sir.
Now look at this. This is the laser path going like this. Okay. So this, you consider it as a straight line. You consider this as also the straight line part of a polygon. So this is one polygon, this is another polygon, this is another polygon, right? 4 polygons are there in this case. First polygon, this intersection we can calculate. So this is intersection number 1. Okay. This is another intersection number 2. Intersection number 3. Intersection number 4, like this. So on first intersection, your energy source will be switched on. Okay. So up to this point, and the second energy source, second intersection point, your energy source will be off. Can we make this arrangement on a machine? A program, we can write a program so that alternatively it is switch on, switch off, on, off, on, off, on, off. It will continue. So first point, it will on. So the laser is start solidification, right? Second point, it is off. So no solidification. Third point, again switch on. Okay. Right. So first point, second point, third point again on, fourth point again off, fifth point again on, sixth point again off, 7 point again on, 8 point again off. So this area and this area will be served. Is that clear?
Yes, sir. Yes, sir. Very clear, sir.
Right. So that is what I am trying to explain in this entire session. I have beforehand shown you how the commercial machines are working, whether it is a powder based or the polymer based, solid based. Right. Now we are trying to melt the aluminum and deposit in same way. So what happens required, that we require our own machine development, own control development, right? I hope in further sections, Dr. Sachin will take you more on sensors and actuators and CNC machines, right? IoT kind of thing. So you can see the programming you have to do, and that programming you have to connect with the hardware. Okay. So this one. Now see how this is generated and taken into this. See the next slide. You see over here the same way. Here your switch on, switch off. So this area you have already marked, which is going to be solidified, right? Solidification. Remaining area laser will fell down. No solidification. Means it will be switched off. Is that clear now? The last figure is clear now?
Yes, sir. Yes, sir.
Okay. So see here, otherwise we have the commercial softwares. We can do this all slicing. Let me show you. How many of you are aware about the magic software? Quickly, you can type in the chat box or say yes, no. Anyone? so that I will go to the magics, or we can skip also. No comments? Anil Shah, are you saying that you are aware about the magic software? Oh, time spent 410. Okay, this is the previous comment. Okay.
No, sir. No, sir.
No, sir. Dr. Narendra Kumar, no, sir. Jitin, I'm not aware of that. Okay. Let me, I'm not going into the detail of the software, but I will let you know what we have done through MATLAB. So I will run the MATLAB as well as the SolidWorks, both. Okay. Sorry, in this magics as well. Okay. Because we are running short of time, I will let you know how we have done this. And if time permits in some other session, we will discuss more detail on the ball screws, actuators, sensors, so that how we control our CNC machine. Let me load a part over here. You can see over here, right? I'm using this part. You can see here, there are 3 spheres inside each one. Is it visible, right?
Yes, sir, it is visible.
Okay, right now I will tell you, suppose this is what we do. This is the shaded mode you are seeing. This is the wireframe, and this is the solid model. Now you see the triangle. What is there? This is the STL file, and everything is kept into the triangles. You can see on my screen that you have all the surfaces are designed like in the triangle. Okay, everywhere there is surface. And why we do this triangulation? Because just we wanted to facilitate the slicing process. Okay, so that's why we do the tessellation or triangulation. Okay, now let me share and set. Let me show you the section. Can you see now the part is section, cross section? Can you see the red color is the inside picture is showing, and the blue color contour is there visible. You can see over here the car is the visible contour. Okay, keep on typing yes, no, okay, so that I can quickly get the response, and that will motivate me to move further. Yeah, very nice. So you see here, the moment I start moving in the vertical direction, see what is going to happen in the first slide. See, you receive the circle and the moving on the top side. You can see here, that is somebody told na, that is the contour at a specific slide. You see here the contour at a specific slide. At this stage, you see only the spring is going to build in this way. Right? See here, the first sphere is built, second sphere, third sphere, right? And from all the triangles, they are connected and converted into a logical sequence. So we have the closed contour. That requirement is that the contour is a closed contour one. Open contour we cannot accept. Okay. And you see here, the 3 spheres are built without touching each other, without joining each other. So now you know about the SLS process. So what is actually happening? SLS process, in between the first contour and the second contour, unsintered powder will provide the support. You can see on the screen, third contour, second contour, you see it is in the air. It is not connecting with anywhere. Okay, but it will still be built without any joint, and it will continue to build like this. See, the first sphere is completed, right? You can see over here. I'm trying to slowly move. I hope you can see the movement of the sphere. Okay, then we continue. So what will happen? Second sphere built now, third, second, and finally. like this, and your part will be bold, right? And this is the section. This is what we have done in the MATLAB. Okay. So at this stage, if you have any other query, then we will switch over to back to the presentation mode.
There is no support material in case of SLS. The powder that is supporting actually, could it be used or waste?
Very nice. This can be reused, but we need to mix with some fresh powder as well. Means not whatever you have used the material, you can reuse it, but with some percentage of the fresh material. That is technically we call it as a refresh rate. So some 60-70 ratio or 60-40 or 70-30 ratio, we have to take it back so that we can reuse. Because otherwise what happens, its neck formation capability is gone down. So two particles are there, but they will not form the neck. They will not join. So make that joining capability of the powder remain intact. We have to put some fresh powder also, right? That's the requirement. Remaining things can work. Okay, now look at this. This is the STL file. I will show you this into the MATLAB. This is the background. You can see here the program written into the MATLAB so that this STL file can be read. And this is how, if you open a STL file, because the short of time, I think we have to bind by 4:30, 4:40. Your next session is at 5 p.m., right? So you can have 10-15 minute break. So I'm not opening the text file, but you can see on my screen, right, how the STL file look like if you open it into the notepad. See here? Let me see. If I hyperlinked it, I will open. Yeah. This is the cube file. Okay, I'm opening it into the notepad. You can see here, this is the solid cube. SolidWorks से हमने इस cube file को export किया. What this contain? The facet normal
and the vertices.
So Cx, Cy, Cz and outer loop x1, y1, z1, x2, y2, z2, x3, y3, z3 means three vertices and the facet normal. Okay. Somebody I think saying same way.
Yes, sir.
Right. So this file, you see there is a difference in the syntax. This file we have exported from the SolidWorks. The same time you see this file we have exported from the Magic. So here the scientific units are there. Here the decimal units are there. Look at this solid facet normal 1, 0, 0, 5, 5, 5, minus 5 because we have taken the 10 millimeter cube which is centered at origin. So that's why all the sides are becoming 5, 5. You can see on this screen. Let me see, this is the 5, 5 and this side 10, 10 because I have taken this time the cube corner at the 0. So the dimension will become 0, 10 or minus 10 or whatever way. And here the 5, 5, 5. Okay, so that's the way. This is how you can open the STL. Now, I hope you can understand for an STL file, you may not require the SolidWorks or CATIA, Pro-E or Vision 360. If you are good in designing, you can type in the MS Word, say dot extension STL file and you can use it. Or you can add it in this notepad and change the dimension. So your geometric model will change. Okay, look at this. The same model is there. Can anybody guess? This is representing the cube. Can anybody represent how many paragraphs like this would be there in this file? One paragraph is representing one facet. And cube will have how many facets?
Depending on whatever layer thickness you have chosen and what is the height of the...
No, not layer. No. Let me correct. The facet is nothing to do with the layer. Right? Okay. This is the solid model. which you have converted into the STL file. So everywhere you have here the facets. These are the facet. So this is the one facet on the top, or you can say this is the facet.
Okay.
Got it? So this is the facet, this is nothing. Now the layer will come, this is one facet, right? So what happens? This is actually one square shape, but converted into one and two facet. Okay, because we have done the tessellation. So this volume has to be closed, as well as this and this both are making it as a solid model closed volume. And one square facet is converted into two triangular faces. So there are two triangular faces. Okay. Now you go for the intersection. So you will receive this point, this point, this point, this point, and this point. Got it? Then you are going to join them like this, 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 this. But remember, these points are not in a sequence in the STL file. This triangle can be 1, this can be 2, this can be 3, backside may be 4, this can be 7. So in a sequence, you get 1, 2, 3 side. Then you need to identify which point has to be connected with which point. Like this. Got it? Clear? So that is the how many? 1, 2, 3, 4. Kitna hoga number in this cube? How many facets would be there?
12.
16, sir. 16.
Anybody else? Anybody else?
12, sir.
12 facets would be there. Very nice, right? Then we start. 5 बजे 5 बजे आपको मैच चल रहा है अभी. So got it? This is the way we have done the tessellation, and that tessellation will facilitate us to get the contour information, right? This STL. Seen this. Another example. What we have done? You have exploded view. So all these triangles are separated, right? This triangle. Then the intersection. So you got this point, right? Individual triangles. Okay. So this contour information you are going to receive. Okay. Now this time I am not going into much detail, but you can see over here with this contour information, you will receive this. So this is the contour information at that particular height you are getting. Since it's a cube, so everywhere you are going to get the square, but the position of these points will be keep on changing. Corner point will remain same, but these mid points will be remain, position will be changing because this is on this diagonal line. So here, 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 it will move on. Okay, clear? So this is how we proceed with the tessellation and the contour generation. Right? Then we have to generate them in a logical sequence. So logical sequence, you can see over here, we receive this point, right? X, Y. Forget about the Z, because at Z is the showing height. So X, Y, head and tail, 0, 25, 0, 0. Start point is this, end point is this. Okay. Then start point is 50, 50, end point is this. So what actually we require? We have to connect them in a logical sequence. What we can do? Suppose this line is there. This line is there. This is 1, 2. This is another line. Say 7, 8. Right? This is another line. Say 5, 6. So what you will see where this 2 is ending, where this 2 is starting. Now there may be another line somewhere here starting 2, starting to 3. So you can connect this 2 with 2, this 3 with 3, then 6 to 7 like this. Okay. So this has to be connected in a logical sequence. So what we will do, you see here, this is starting 0, 25. Kahan ja raha hai? 0, 0. So you look for this 0, 0 where a new line is starting from this 0, 0. Can you see? Means this 1 has to be connected with the 8. Now this is ending at 25, 0. Okay. So 25, 0. Can you search here somewhere 25, 0?
4.
4. Very nice. So this has to be now here. This is now connected to be 4. Okay. So in this way, what you ask in the very early, how we are knowing which area to be solidified. I am talking the same algorithm. Here you are going to identify the one contour. You can eliminate that contour. So 0, 25, 0, 0. Now it is connected with this 8. Right? Then 8 is connected with the 4. And continue. You can see on this screen and you can understand that how we have connected these many points. Is this okay? Shall we move forward?
Yes, sir.
Yes, sir.
Now look at this one example of the pyramid P1, T2, T3 and P1, P2, P3, P4, how we generate the contour information. Okay, based on this contour information, our next task is, suppose you this contour information you got. Okay, this is the contour information you got. Now within this contour, this is the nozzle path you have to generate. So what you can do for this generation of nozzle path, you can draw a straight line, find out this intersection, offset it by whatever the dimension, say 5 millimeter you want to move upward. So the second point, then you draw again parallel line, find out the intersection point, then again 5 millimeter, then again intersection point, right? And the same thing you can do with the programming with the MATLAB or Python or whatever way you would like. Okay. So entire thing you can done with the MATLAB and how to write that information. What actually it is? A point means XY. A point means XY, right? What 3D printing machine is required?
G code.
Suppose
X and
this
Y
machine
Z
is
coordinates.
you. Yes. So now you got the XYZ of a contour at a particular height, right? Same with this information you can write over here, and this program you can send to your 3D printing machine. You don't require any open source software, any commercial software or anything. You can do the entire thing with your MATLAB. This is what I shown you in the case of a computational part. Let me take you to the MATLAB. I was kept open MATLAB. Where is this? Yes. Okay, not taking much. I am taking only one STL file running. Let me open an STL file. Since we are talking about cube, so let us take a cube. Okay, cube SolidWorks. Which file I have taken? Yes. You can see here, this is the cube file I have shown you. Now you can see on my screen, this is the MATLAB. Okay, so you can see the 12 faces are there. And what happens? This file was written in a text file. So we have read in this text. You can see here the C++ programming structure on my screen, right? So we have gone through this text file, read every line by line, and get this numerical information stored in a matrix form. So look at this. There are PTF 12. 12 means 12 faces. 11th face, see from here. First phase, surface normal, coordinates, 3 coordinates. So this is the first phase. Second phase, third phases, 4th, 5th, 6th, 7th, 8th, 9th, and up to 12 phases, right? So this is the information we have collected. Now we went into the some other mathematical programming and algorithm to have it cross section. Okay, let me show you crack repair. I'm not going. Let me have this file. So this is a big file, big large program where we open an STL file, cross section it, arrange them in a logical sequence. Okay, so since we talk about the cube, let me open the cube file only. Okay. And this data we will send to the data file. Let me take an STL file. Okay, let us take a cube file. Okay. So that this is the cube file, and you can see over here, the geometry, my program is already knowing starting point is 0 and the maximum height is 50. Let the generate the same data. So let me cross section at 25. Okay. Let me put the enter, and this is the MATLAB you got. Oh, sorry. What we have taken? Oh, sorry. We have taken the cone.
Yes, you have
We
taken
will
code.
regenerate. Yes. We will take it the cube again. Here are the so many points, so understanding may be difficult, but we will take it the cube as well. Okay, so this is the contour information we got. Let me close all. And that's the because so many hundreds of points are there, so that's why it is taken. And you see these many metrics for generated for the cube at 25 height, right? And then all the points are logically connected. You see here around 55, 56 points are generated. Okay, let me run the same program again for cube. Okay. So 0 to 50, let me take again 25. See, this is the STL file, right? This is the contour. You can see head and tail both. Now you see on the bottom side, this is you got the head and tail, new segment, old segment. You remember this? We have seen this in 25, we have arranged, okay? 50, 25, 50, 50 like this. Clear? That's the same thing I have shown you in the presentation. Right now you can look at it here, the same thing we can have. Let me put the close all. Okay, and this information is sent to this file, data. Whatever the points you have generated, they are stored over here, right? This ये पीछे नीचे पॉइंट कौन के आ रहा है, राइट? तो मैं एक बार इसको डिलीट करके फिर से भी जनरेट कर सकता हूँ. Let me delete this file. Okay, we have deleted this data XLS file and will regenerate and open the same file for cube. Okay, and this time let me put a height 30. Okay, see the STL file. See here, this is the contour generated, right? Now look at this, the data file. Okay, it is generating the data file. Okay, now the data file is regenerated. Open outside the MATLAB. You can see over here. This is the information, contour points generated by the 8 points by the program, right? These program, we can directly take it to the lab. So you can see, let me run this nozzle path program. Right, this nozzle path will go to this data file, read those 8 points, right, and then generate the nozzle path. It will ask some information from the user and then generate the nozzle path. Okay, so this nozzle path generate and it will be written in this G&M code file, right? And on the bottom side you can see this file, G&M code nozzle path. Okay, this is the path, this is the file. So let me delete this first so that we can generate the fresh file. I have deleted this file. You can see here, the file is deleted. Now we will run this nozzle path. So it is asking for input size. You can see this is the contour you have generated, right? 0 to 50. Okay. So let me take the say I have taken 4, the step size. Temperature at his bed has to be heated initially, let's say 220. Temperature at which nozzle needed to be heated initially, say 240. And you see here, this will be generating the nozzle path. Got it? This is the nozzle path generated, and that G&M code is again generated. You can see over here, this is the G&M code file. Let me open this outside the MATLAB. See, this is the part program, it has been generated. This program you can directly copy to your 3D printer, and that the nozzle path will be generated. Got it? Is that okay? Okay. So, okay, this is all about how you are going to generate the data. Okay, then what happens? Initially, we have taken this to the conversion of our CNC machines, right? And we have developed the hybrid additive subtractive manufacturing system. So what we did in this setup, we have developed an extruder head. Okay, in this extruder head, see this extruder head. Here is the resistance heater, just like your polymer printing. And here is the milling machine head. And this milling machine head, we have point this hopper. So instead of wired spool material, the small pellets of the material can be used here. So no need to have the material in the form of a wired spool. Okay. And this will be heated, extruded, and run on the material, run on the CNC machine bed. Okay. Let me run this video. You can see here how we have deposited the material on the CNC machine. You can see over here, after a lot of experimentation, we have developed that so that it can smoothly print the part. Right? So that is the part you have seen, which we have done on this. On the same setup, we have changed this extruder head. This is the automatic tool changer is there. We can exchange this extruder head and we can put the material removal tool on the same setup without removing this material. That's why we call it hybrid additive subtractive. Okay, let's see this video as well. Like, so you see how we are removing the extra material which is deposited on the same setup, right? I would need a response over here. Have you seen both the video? removal and the joining, additive and subtractive both. So Jitendra, yes, 1638 responses. Okay. Anand, Anil, Ulhas, 4 responses. Quick responses. And the same setup, we are able to deposit the material and remove the material, right? And yeah, one more, yeah, Rumukh, fine. So see here, yeah, Padma, okay, fine. Now look at this. This we have further developed the MATLAB code. So on the same that we can generate for additive manufacturing and subtractive manufacturing. We can give different parameters, import the STL, do the slicing, generate the toolpath, GMN code, and STL file, code, internal contour path. We can do all in one. And that GMN code file can be directly sent to your 3D printing machine. Okay. Similarly, on the subtractive, cutter diameter, step over, etc., we can say toolpath, GMN code. So this is the subtractive process. So from same we can generate both the things. This is for subtractive and for additive both. Okay, and that allow us to make many experiments because everything is now developed by ourselves. Starting from the STL file, slicing, everything we can do it by our own. So we are not at all dependent on any other system. Okay. So if you have any question at this point, you may please ask. Then I will tell you for the induction conduction based metal additive manufacturing system, which we are currently working on it.
In the hybrid method, do we need to change the tool head? That is what you said, sir. Am I right? Tool head you have changed, once the additive manufacturing is done. Did you change the tool was fixed again? Tool head for subtractive manufacturing, if I'm right?
Yeah, somebody was asking something.
Sir, in the hybrid, you changed the tool head, right, sir? It was the tool head was changed, right, sir? When it was doing
Yes. On the same setup. If you want
Yes,
it to be done on the same setup, you can change because we have converted
that is
our
manual.
Okuma
Is it
machining
manual
center.
or manual?
Both way
Automatic.
possible. If you want to make it through automated command, you can give through the command, right? And if you want manually, so there is M06, M08 codes
Yes.
are there. You can just change the tool.
Thank.
So that also follows in the same path.
No. Because initially what happens from bottom to up, you have deposited the material. When it comes to remove the material, that it is going from top to bottom. And further, this is up to you what kind of GNN program, what is the tool path strategy you want to use. So you can remove the material in your own way and you can deposit the material in your own way.
Thank you, sir.
So the removal toolpath can be different from that of the deposition toolpath, is it, sir?
Yes, you can use a different toolpath for both way. Means the path strategy can be different. Like for deposition material, you can use like this. Okay. Removal material might be your strategy will be like this. So anything depending on your choice or requirement, you can do it, or you can use the same also. There may be many possible ways. There may be a gap also. Say, for example, this is gap. So your tool path will be like this. Okay, then this area you have to restart. right? The same way you can also take up in this way, there is a gap. So you can come here, lift the tool, move like this. Then lift the tool, move like this. So depend that strategy you have to formulate what way you want to do it, right? Okay. Now look at this, what is happening with this, the two methods we have taken up. Okay, so yeah, somebody has typed in the chat box. Okay, what material used for nozzle, sir? Right now we are using brass. Okay, now look at this, what is the happening with the energy source? Right now you have the laser source, I have shown you the electron beam, the arc and electric arc system, right? Now what I am proposing today is the induction heating. As you know, the resistance heating will take time. Electron beam is very costly. So we are going to induction heating. And you know the induction heater, every household is now available. Okay. So what we do in the induction heating principle, you see here, this is the induction coil. This is the extruder material, or you can say nozzle. So extruder is there, induction coil is there, metal print. Okay. We are already running short of time. Okay. Dr. Sachin, 5 p.m. whose session is there? You see here, this is the current flow copper coil, right? So induction heating coil is there, the current flow is going on. In this current, what happens? The magnetic field will be generated, and this we put the core. That is the extruder head. So because of this obstruction in this magnetic field, this core is heated, right? Okay, so that is what we are going to apply for the additive manufacturing. Now look at this. Initially, the long back we have started work. We have started with this small prototype. Then we have taken this tripod additive manufacturing system and we have put our setup over here. Right? And from this, the material is extruded. Right? From this, and here it is material deposited. This is the one. Right? Look at this, the later one, the next we have built on this rectangular base system. This is the aluminum wire feed, just like you see in any commercial 3D printer, which works on the ABS material. Okay, so this is the aluminum material. This we have designed typically to push this wire, aluminum wire through. And here you can see the extruder nozzle is there. Below you can see this is the CNC machine setup, which we have designed. We have all this hardware we have designed for these guideways, then this ball screw mechanism, then this software mechanism, this Mac 3 open source software we have used. This is the induction heater. From this induction heater, we have to supply the current. This is the 200 ampere, around 56 hertz current is required. Okay, this is the control interface, induction heater. This is the PID controller to control the temperature or develop the cut mechanism. Right, and this is our final system which we are working. I will show you some of the videos over here. Right, this is then we initially, this is in the open environment, then we find a lot of oxidation is there. So to stop that oxidation, we have taken into the closed chamber. So this is inside, this is the vacuum chamber we have developed, and here is the motor. Every system is there inside this. I'm using my mobile data, and if somebody is calling now, that might be.
No problem, sir. It's happened.
Okay. So see, this is the different machine component that I have shown you. The extruder head we have used. This is the coil system. You see, this is the coil, induction coil, extruder head. And this is, you see, heated. This very less than 1 minute, we reached it to the 600 degrees centigrade. Then you see bottom also on the heating bed, you require to heat it. The challenge is once you start heating on this system, below is the CNC system. So if you take this to the 600 degrees centigrade, below side, the ball screw mechanism, the motor and the connecting wires, they all will burn. So that has to be quickly, very rapidly to be cooled down. Okay. So we initially put the insulation, but insulation was not sufficient. So we have put here the cooling channel. You can see over here, there is a water tap. So inside this table, there is a cooling channel and water flows through this channel and out from these two channels so that the blow side machine system can be protected like this. The wire material, and here is the semi-solid extruder, then the heating bed, then this is the material deposition. So this is the wire up to quenching, then this is the heating, and then heating bed here, then the air cooling up the part. So we can have this part in this position. Now let me show you this I have shown, I think, in the very first. Okay, let me take you to another video. So lot of experimentation, simulation are required here. I'm not taking into much detail at this means how long this will give you the uniform heating or uniform magnetic field and how many number of coils. We have taken the 9 coils. So you see here, we have done the simulation up to 13 coil. So starting from first coil, second, third, fourth, and here you see there is not much difference in this graph. Okay, so we have opted for this 9 coil system. Okay, so we have, because you cannot put n number of coils into there as well. So 9 coils is there. Okay, then we have developed this system. Find out. Okay, so that's PID controller we have put. So this temperature can be restricted to the 600 degrees centigrade. Okay, bed temperature. Then this is the different simulations, boundary conditions to put current 200 ampere, 55 kilohertz, radius, etc. So we have to also find out what is the correct radius, then what is the coil shape we have to take up, right? And this coil shape, we have to find out which the temperature distribution. This is in the conical helical, and this is the helical coil system. We want this, that towards this area, temperature should be high, and toward this area, the temperature will be low. So like you see the different helical coil, conical coil, square coil, oval coil. Then we have gone back to the console and we have done the simulation and identify the optimized coil shape. This is the optimized coil shape, right? So console gives you what the distance you can take for the different coil systems. Okay. So for developing this coil shape as well, we require the 3D printed support mechanism. Otherwise, by simple tools, you cannot have this brass tubes without bending or without damage to be in different radius. So this 3D printed material we have developed, and this is the final coil. Let me show you. This is the final coil. Okay, and with this coil we have taken up. So you see this material deposition standard taken up, and this is the final developed system which we have in our lab. If time permits, maybe Dr. Sachin can show you through the video call. You see here, this is the deposition going on. See the deposition going on. Is this okay?
Very thick deposition, sir.
Pardon?
Very thick deposition. Layer thickness
Yes,
is very.
yes. Right now it's yes, absolutely fine. It is the problem. You see, very thick deposition, and still we do not have any solution for the overhanging features. Like in polymer, we have this is not we have. You can see on the top the deposition going on. Still lot of break are there. Like polymer, I have shown you that still we are struggling to get the very much controlled. This is the one full machine video. You can see here the control system.
I think you're still in primitive stage, I think, sir, because material strength
Pardon?
and all. I think still you are in primitive stage.
Yeah, we have not at all moved to that part actually.
Yes, sir.
Because the first is the challenge is to ensure the continuous printing and getting
Yes,
the
sir.
proper print for additive manufacturing.
Yes, sir.
That see here the deposition you can see. It is slow but steady and consistent. But you require the all information what we have discussed in last 2 hours.
It looks like a standard coil here, sir. Actually.
Yes, this experiment I am showing with the standard coil. Yes, this is the helical coil.
Right, sir. Right.
Let me show you in some video. So this is the full-fledged system, right? And this is the current scenario where we are looking for some more support, more research into that to have the full-fledged metal deposition system in the wired form. Right now, it's not available, right? So, Dr. Sachin, with this, I would like to say thanks to you and the organizing team and all the participants.
Thank you very much, Professor PK Chen. It's really nice to see a lot of research work and the background related to additive manufacturing, SLS methods, and especially the induction-based extrusion additive manufacturing. So, yeah, because I have seen these machines very closely. So a lot of research work has already been done by the professor in this direction, and still gaps are there where the further research work is needed. And we believe we will have your more lectures in this FDP. And I know that you are very busy in a lot of administration and research work, but considering the enthusiasm of the participants, I believe Professor will give another pre-session whenever he's comfortable. Thank you.
Sure, sure.
Thank you very much. Thank you very much, Professor.
Thank you so much,
Okay,
sir.
thank you. So I think we have already taken so many questions during the session, and you may share my details if any participants want. We would love to connect, right?
Yeah.
All these things are published material. You will find my research papers, and if required, I will share the PDF of my slides with the Dr. Sachin. You may take.
Yeah. Thank you. Thank you very much, sir. Thank you very much.
Okay, so please allow me to leave the meeting. Okay, thank you.
Thank you, sir.